The Convair F-106 Delta Dart was the main all-weather interceptor jet of the U.S. Air Force for almost 20 years. Designed from scratch as the so-called, quote, ultimate interceptor, pilots would reportedly fight each other to fly it. It had one mission, and it had to be fast. With a sleek body and missiles tucked in an internal weapons bay, it could reach speeds over 1,500 miles per hour to intercept the Soviet Union's long-range bombers. And as one bizarre incident would show, it could sometimes fly and land on its own. The Delta Dart began in 1949 as Project WS-201A. The plan called for a fighter interceptor jet capable of carrying air-to-air guided missiles with an all-weather search and fire control radar, all while being able to reach supersonic speeds. For the weapons guidance, the Hughes Aircraft Company was awarded a contract in 1950 to develop a radically new fire control system. In theory, the system would be capable of automating many of the plane's flight and attack functions. A mock-up with the planned layout of the MX-1179 fire control prototype, renamed as the MA-1, was approved in December 1955. With sensors, it was essentially a 2,500-pound computer, although the prototype was touted in a radio and TV news article as being, quote, small enough to fit into a 21-inch table model television cabinet. The airframe would need to be built around it. The contract for the actual airframe was presented to Lockheed, Republic, and Convair. Convair won the proposal because it was closely related to the earlier development of the Delta Wing XF-92A. This experimental design would eventually be incorporated into the F-102 Delta Dagger, F-106 Delta Dart, B-58 Hustler, and the F-2Y Sea Dart. The Air Force and managers at Convair were convinced that the Delta Wing configuration was the best answer to issues that usually complicated supersonic flight. Delta Wing designs went as far back as World War II, when they were first proposed by Germany's Alexander Lippisch. The jet was initially an improved derivative of the F-102 Delta Dagger, with the designation F-102B. The Dagger was supposed to be able to fly at supersonic speeds from its inception, but problems plagued its development. Eventually, it underwent such extensive changes that in June 1956, the redesigned version finally emerged with a new name. Confident that the aircraft's design would accommodate the new weapons system, an extended production contract was sent out. Often referred to as the ultimate interceptor, it had the primary mission of shooting down enemy bomber aircraft. It became the last specific interceptor in the U.S. Air Force. The Air Force had wanted the interceptor to be operational by 1955. Still, by the end of 1952, it was already clear that neither the engine nor the fire control system would realistically be ready by then. The program would run into additional delays and trouble. The Delta Dart's ejection seats proved to be one immediate problem. The first model fitted to earlier models of the F-106 was a small variation of the seat used by the F-102, called the Weber interim seat. It was a catapult that used an explosive to propel it away from the aircraft, but it was inadequate for ejections at supersonic speeds. The Convair Industry Claw Escape System Committee replaced the Weber interim seat. It was designed with a supersonic ejection in mind, as the F-106 was expected to reach Mach 2 performance. But the ejection process proved too complicated for pilots, and some unsuccessful attempts at ejection even resulted in tragedy. The third and final seat for the Delta Dart was the Weber 00 rocket catapult seat. Weber Aircraft Corporation designed a seat able to operate at 690 miles per hour. The reasoning was that high-altitude supersonic ejections in the Delta Dart would be rare. Ejections at low altitudes and low speeds were deemed more likely. The Weber 00 seat was determined to be good enough and was fitted to the F-106 after 1965. The Delta Dart was explicitly designed as an interceptor, powered by the powerful Pratt & Whitney J7517 engine. It was also amongst the first aircraft to have semi-autonomous military weapon platforms. The F-106A had a length of 70.7 feet and a wingspan of 36.29 feet. Similar to the F-102, the F-106 was designed without a gun or provision for carrying bombs. The Delta Dart had its missiles hidden in an internal weapons bay for a cleaner supersonic flight. The Hughes MA-1 electronic fire and control system worked simultaneously with the semi-automatic ground environment defense system. It took control over the plane right after takeoff and guided it to a proper altitude and later attack position. This system enabled the aircraft to lock and fire the enemy's weapons and return the jet to its airbase. The pilot would then take over control for landing. Some armaments that were compatible with the Delta Dart included the Douglas Air-2A Genie rocket with a nuclear warhead and the AIM-4 Falcon missiles. The first Convair F-106 finally flew in late December 1956, and deliveries to the Air Force began in 1959, but ended only a year later. In December 1959, Major Joseph Rogers set a world speed record aboard a Delta Dart with 1,525.96 miles per hour at 40,500 feet of altitude. That same year, Charles Myers also flew an F-106 at 1,544 miles per hour. Initial testing revealed problems with performance, engines, and avionics, which threatened to shut down the F-106 program entirely. But rather than pull the plug on the Delta Dart, the Air Force decided to order substantially fewer of them than initially planned. The initial F-106A request was reduced from 1,000 aircraft to only 277, plus 63 two-seat dual-control F-106Bs, outfitting 14 squadrons and a training unit. The reduced order also considered the ever-evolving Soviet threat, which had shifted from an earlier emphasis on bombers to ballistic missiles. During its long operational life, the F-106 held the record for having the lowest single-engine aircraft accident record in all of Air Force history. Even today, the Delta Dart could hold its own in the fighter training and combat area against current jets, and its speed record for a single-engine jet still stands, quite an accomplishment for a plane that's over 60 years old. The Delta Dart served in the US, Alaska, and Iceland, as well as in Germany and South Korea for brief periods. While in service, the F-106's official name, Delta Dart, was rarely used, as it was universally known as the Six. Although the Delta Dart was contemplated for service in Vietnam, it never saw combat. The Canadian government briefly considered purchasing some, but it was never officially exported to foreign users. After resolving its initial problems, particularly its faulty ejection seat, its exceptional performance made it very popular amongst the Air Force pilots. The F-106 was continuously updated, with improved avionics, modified wings, an infrared search system, an arrestor hook for landing emergencies, and even streamlined supersonic wing tanks. Initial air-to-air combat testing suggested that the Delta Dart was a fair match for the F-4 Phantom II in a dogfight. It had a superior high-altitude turn performance and better maneuverability. But the Phantom II had a better radar, which was operated by an additional crewman, and could carry up to 4 radar-guided AIM-7 Sparrow and 4 infrared AIM-9 Sidewinder missiles. The AIM-4 Falcon missiles, which the F-106 carried, were at a disadvantage in comparison. The Six would likely have not fared well in Vietnam dogfights. In the early 70s, several F-106s were upgraded in a project that involved giving the Delta Dart a new canopy without a metal bracing, improving the pilot's visibility. In 1981, the F-15A Eagle started replacing the F-106. Some of those aircraft were converted into drones and changed their names to QF-106A. 6 Delta Darts were passed on to NASA for experiments. A test between 1979 and 1991 used a modified F-106 in research programs for maneuverability improvements in jets with supersonic engines. NASA engineers modified a Delta Dart for the purpose of lightning strike research. Between 1980 and 1986, the F-106 was struck over 700 times without damage. The Eclipse project, which ran in the late 90s, used 6 F-106s modified into drones. The project's main objective was to tow a modified QF-106 aircraft with a C-141A transport aircraft, all while still flying. The test proved the possibility of towing and launching a space launch vehicle from behind a tow plane. The F-106 remained in service in several USAF and Air National Guard units. The last Delta Dart was retired from the 119th Fighter Interceptor Squadron in 1988. The infamous Cornfield bomber has become a staple of U.S. Air Force lore and the most famous Delta Dart of all time. On February 2, 1970, the Iron Men, 3 F-106s with the Fighter Interceptor Squadron, took off from Malmstrom Air Force Base near Great Falls, Montana, for an air combat maneuvering sortie. During the mission, one of the aircraft departed from the controlled flight and began flat spinning. The aircraft's pilot, Captain Gary Faust, wasn't able to return to controlled flight and had no option but to eject. But the story didn't end there. The aircraft's weight and balance were altered during Captain Gary's ejection, so much so that the plane recovered from the spin by itself and resumed into a stable flight. The now unmanned F-106 flew off on its own. All the squadron pilots assumed it had crashed somewhere beyond their range, exploded, and a shallow crater full of debris was somewhere around in the Montana countryside. But the plane had defied all logic and belly-landed in a snowy field near the town of Big Sandy. The local sheriff received a call about an airplane with its engine still running, sitting in a cornfield. He advised to let the engine run until it ran out of gas. The Sacramento Air Logistics Center at McClellan Air Force Base in California dispatched a depot team to the unlikely scene. After assessing the situation, the team discovered the wings of the airplane were still in flying condition. They were removed, and the rest of the plane, including the fuselage, which had sustained minor damage, was disassembled and sent back to California by train. The aircraft was repaired and eventually returned to service. It's currently on display at the National Museum of the U.S. Air Force. The Vought F-8 Crusader is perhaps best remembered for having many nicknames. Thanks to its supersonic speed and how it could safely take off even with its wings folded, pilots liked calling it the sports car of the Navy. Deck crew members fondly referred to the aircraft as the Gator, because the engine's air intakes were not very high above the ground and it had the power to suck in a man. Crusader also had a fruitful record during the Vietnam War. After shooting down 18 North Vietnamese MiG-17s, it earned the legendary label of MiG Master. And since it was the last U.S. fighter designed to carry guns, 4 20mm autocannons, the F-8 is also remembered with the nickname the Last Gunfighter. The Crusader was built when the United States wanted to show off their air superiority. And although history has sometimes neglected the F-8's role in favor of valorizing the F-4 Phantom, this fast and deadly jet is still considered one of the most remarkable aircraft of its generation. The Crusader was such a beloved aircraft that it inspired its own saying, "When you're out of F-8s, you're out of fighters." After the Korean War, the U.S. Navy decided it needed a fighter jet that could carry 20mm autocannons, as standard machine guns were proving no longer sufficient in aerial combat. In September 1952, the Navy announced a requirement for such an aircraft capable of landing at 100 miles per hour or less. Vought, led by John Russell Clark, presented the V-383, later acknowledged as the F-8 Crusader. The aircraft had a powerful Pratt & Whitney J57 turbojet engine that produced 18,000 pounds of thrust. This made the Crusader the first fighter jet in the U.S. arsenal, able to climb straight up and reach a speed of 1,000 miles per hour. The plane also had a long range and could fly through any weather possible. Most notably, the aircraft had a variable incidence wing that pivoted by 7 degrees while landing, which gave it a higher angle of attack without compromising forward visibility. The Vought F-8 won over other designs like the Grumman F-11 Tiger and McDonnell Douglas F-4 Phantom II. On March 25, 1955, test pilot John Conrad took the aircraft on its first flight. During that maiden flight, the aircraft exceeded the speed of sound. 30 days later, after a seamless development process, the second prototype also had its first flight. Prototypes of the aircraft immediately started setting records. In 1956, Navy test pilot R.W. Duke Windsor and the Crusader broke a national record after flying at a speed of 1,015 miles per hour. On June 6, 1957, the aircraft covered 2,200 miles from the west to the east coast in only 3 hours and 28 minutes. That same year, aboard an F-8U-1P version, Major John H. Glenn performed the first supersonic flight from California to New York. This journey took 3 hours, 23 minutes to complete. Manufacturer Chance Vought also worked on the prototype of the Crusader III, which would become a successor of the F-8 program and a competitor of the McDonnell Douglas F-4 Phantom II. The Crusader III was larger than its siblings and had a more powerful engine. During its debut flight in 1958, the aircraft's performance was outstanding. However, the program was scrapped to prioritize the Phantom, which was considered tougher and more versatile. By 1957, the Crusader had been sent to the U.S. Air Force and the Navy. The Swordsman Squadron was the first team to fly the plane, which was later deployed to the Mediterranean that year aboard USS Saratoga. The F-8 was also sent to the VF-154 Black Knight Squadron, based at NAS Moffett Field in California. Despite the hope for a slower landing jet, the Crusader came down surprisingly fast. Pilots needed considerable skill to land safely. Aircraft carriers would often be sent barreling full steam ahead to help lower the relative landing speed. Takeoff was also fast and challenging for pilots, who had to wrangle an aircraft so powerful that it could get airborne, even with its hinged wingtips folded up. As pilot Don Fraser said, quote, "There were no simulators in those days. You strapped it on and hoped you had it all right." The jet was a favorite amongst pilots. but commonly suffered hydraulic fluid leaks and electrical system breakdowns. All this gave the Crusader a higher mishap rate. From the 1,261 aircraft that were built, 1,106 were involved in accidents. The airplane could also be intimidating for the ground crew, who nicknamed it the Gator. Crawling down the engine intake was a scary experience for the workers, who feared being sucked in. It was also positioned quite low. Crews were explicitly told to avoid venturing in front of the plane. Jet mechanic John Borey recalled an incident in which he grabbed a pilot by his ankles as he was getting sucked in by the air intake. The aircraft was top-rated amongst pilots, who liked calling it the Navy's sports car. As General Jack Daly, director of the National Air and Space Museum, said, quote, "Everybody who flew that airplane loved it." Mechanics were also fond of engine runs thanks to the powerful afterburner of the plane, which only had 2 settings, on and off. This could give it an impressive and uncontrolled explosion of thrust that had deck crew members constantly on their toes. Six years after its introduction, the Crusader was sent to the front lines of the Cuban Missile Crisis. In October 1962, the plane was part of Operation Blue Moon, which consisted of low-level photo reconnaissance missions over Cuba. Twice a day, the F-8s would fly from Key West, Florida, to Cuba and back, for the film to be immediately developed and sent directly to the Pentagon. Through 160,000 images taken by the plane, the U.S. confirmed that the Soviet Union was setting up immediate-range ballistic missiles on the island. Later on, they also documented how the weapons were withdrawn. The pilots of the aircraft were eventually honored with distinguished flying crosses. The squadrons received the U.S. Navy Unit Commendation. It was March 1965 when President Lyndon B. Johnson sent U.S. combat forces into Vietnam. Early on, the Crusader became the dominant aircraft, as it annihilated the MiG-17s of the North Vietnamese force. The F-8 excelled at dogfighting, a quality that differentiated it from all other aircraft that flew over Vietnam. The Crusader also carried 32 unguided Mighty Mouse aerial rockets, and an additional 2 guided AIM-9 Sidewinder air-to-air missiles. These qualities even bested the F-4 Phantom II, which wasn't armed with internal cannons, and hadn't been specifically designed for maneuverability. The Crusader was faster, lighter, and could fly longer distances. As historian Barrett Tillman said, quote, "Only the F-8 could be called a true air superiority fighter." The aircraft carried the best kill ratio of the war, 4 MiGs for every 2 losses. Only 4 victories were won with the plane's internal cannons. The rest were achieved with its AIM-9 Sidewinder missiles. The F-8 was extremely lethal against the Vietnamese aircraft, bringing down 19 MiGs during the war. This earned the aircraft the nickname the MiG Master. The plane also served the U.S. Navy and Marine Corps during the attacks against Communist forces in North and South Vietnam. In 1965, the plane was used for Operation Flaming Dart, which consisted of a series of airstrikes against Viet Cong bases, as retaliation for attacks against U.S. Air Force bases and a hotel that housed American citizens. Rear Admiral Bob Shoemaker was flying low on an F-8, while attacking barracks a couple miles away from the demilitarized zone. Shoemaker's plane was shot down, and even though he survived, he was kept as a prisoner of war for 8 years. During the conflict, 170 Crusaders were lost. The F-8 didn't only have a successful story serving the U.S. Armed Forces. In 1962, the French Army ordered several F-8s, which needed to be modified to fit their smaller carriers. The aircraft was also modified to carry 2 French Matra R-530 infrared missiles. The Crusader served through the 70s and 80s, but was involved in only 1 combat interception with 2 Yemeni MiG-21s. In 1983, F-8s escorted the Dassault Breguet Super Étendard fighter jet on its combat missions over Lebanon. They also served the French Aeronavale in missions over the former Yugoslavia and the Adriatic Sea. It stayed in service until the year 2000, when it was entirely replaced by the Dassault Rafale twin-engine plane. The aircraft also served the Philippine Air Force from 1977 to 1991. The government purchased 35 second-hand F-8s from the U.S. Navy, which agreed to train the Philippine pilots. 10 planes were used for spare parts. In 1998, the rest of the aircraft were grounded due to the shortage of parts needed to fix the F-8s that got damaged. The jets were officially retired and sold as scrap after they sustained damage during the eruption of Mount Pinatubo in 1991. In the 70s, NASA selected an F-8A to install a supercritical wing, which reduced the effect of shockwaves on the upper surface. However, the wing increased the operation costs, and soon after, it was considered impractical. A modified version of the Crusader was also used to test a digital fly-by-wire control system currently used by space shuttles. Following the path of its outstanding career, the Crusader helped NASA push the frontier of flight. The Crusader served in active duty until March 2, 1987, when the last of them was sent to the National Air and Space Museum. The F-8 was the first Navy fighter to stay in service for almost 2 decades. Even when it wasn't involved in air combat anymore, the jet served with active light photographic squadrons. Nowadays, this legendary aircraft can be found in museums and private collections. But the Crusaders are continuously overshadowed by the F-4 Phantom, which was less agile than the F-8 but also faster, more powerful, and more adaptable. The F-4 also doubled the operational life of the Crusader and was retired in 2016. However, from the beginning, the Phantom had been designed for interception and engagement with missiles. In contrast, the Crusader had been made specifically for dogfighting. Today, the F-8 is remembered as the last gunfighter, since it was the last U.S. fighter designed to carry 4 20mm autocannons as its primary weapons. It's also considered a remarkable aircraft that had a fundamental role in some of the most important conflicts of the last 50 years. During the first years of the Cold War, the United States Air Force's Strategic Air Command had a simple defense strategy. If the conflict ever turned hot, they would have in their ranks fighter and nuclear bomber planes so fast that they would be uncatchable. It was envisioned that these innovative aircraft would be able to dash into the Soviet Union and China territories at speeds and altitudes that enemy missiles wouldn't be able to reach. To achieve this, they needed an incredibly fast plane with a radical design that could give one hell of a show. As an answer to their needs, Convair gave them the world's first operational supersonic bomber, the B-58 Hustler. The Hustler was the model plane for a new era of fantastic aircraft. With its shiny, attention-grabbing armor, sleek delta-wing design, roaring takeoff, and notorious sonic boom, the B-58 was thought to be an ideal projection of American power and strength. Numerous world records were set by B-58s, some of which still stand. But 22% of the built Hustlers were destroyed in unfortunate incidents. Even the most skilled pilots were terrified to fly it, and the Soviet Air Force threatened its future in combat before it even began. In the Hustler's case, anti-aircraft technology improved faster than its supersonic speed. After an Air Force's Generalized Bomber Study was issued in 1949, Convair, currently known as General Dynamic, submitted several proposals for a delta-wing bomber design. The plane would be powered by 3 General Electric J-53 turbojet engines and capable of flying faster than 1,000 miles per hour at a range of 3,000 miles. This was an ambitious proposal. U.S. Air Force Captain Chuck Yeager had only broken the sound barrier aboard the Bell X-1 2 years prior. But the Air Force was impressed and chose Boeing's MX-1712 and Convair's MX-1626 proposals to go into a Phase 1 study, leaving Curtiss, Douglas, Martin, and North American Aviation out of the project. During this phase, Convair developed several changes to the proposal, such as switching the J-53 turbojet engines with 4 of the newer J-79 models and a redesign of the aircraft body to give it a much narrower fuselage. These modifications made the design for the bomber more apt for supersonic flight and helped to win a tight race against Boeing. When it came time to make a selection, the Air Force reportedly took into consideration that Boeing was already producing the B-52 Stratofortress and chose Convair's MX-1626 to diversify manufacturers. In February 1953, the Air Force issued a contract to develop Convair's proposal, now formally named the B-58. The B-58 Hustler was a delta-wing aircraft bomber, with 4 turbojet J-79 General Electric engines hanging from the wings. This supersonic bomber inherited its delta-wing design from earlier Convair projects, such as the XF-92A and the F-102. The innovative aircraft had some sophisticated and extremely modern features, including inertial guidance navigation and bombing systems. They included recorded messages in a woman's voice to warn crew members of flight circumstances. To minimize overheating while in supersonic cruise, Convair engineers designed the B-58's skin out of honeycombed fiberglass in between aluminum and steel plates glued together. This method would later be used in other aircraft like commercial airplanes. Although the B-58 did not have a bomb bay, it could externally carry a single nuclear weapon with a centerline fuel pod over it. 4 extra weapons, nuclear or conventional, could be carried on external hardpoints if the fuel pod was taken out. But this degraded the aircraft's range even further, as the area for fuel was already small. These containers could also be used to hold cameras and other miscellaneous equipment. The B-58's wasp waist fuselage was no exception to unconventional innovation. Each of the 3 crew members, a pilot, a navigator or bombardier, and a defensive systems operator, had their own compartments. Separated by equipment, the team passed along notes via a string system that ran along the cabin's main wall. Convair engineers were required to create a unique emergency ejection device, as conventional designs from the era weren't suitable for supersonic speed. After a few years, and a few unfortunate accidents, engineers were able to develop a novelty escape pod. It consisted of a protective shell armor that would enclose the seat and control stick with an attached oxygen cylinder. This armor allowed the pilot to continue to fly even when in the pod, allowing him to maneuver into an optimal ejection orientation if possible, and conduct an immediate escape. The capsule could be used as a flotation device if needed, and the crew member could use the shell as a life raft. Also unusual for the period, these innovative ejection systems were tested with live animals, including bears and chimpanzees. The Hustler was relatively small for a bomber, with a length of 95.1 feet and a 56.9-foot wingspan. In comparison, the B-52 was 64 feet long and had a 185-foot wingspan. The bomber's size created one of its most significant weaknesses for a jet designed to infiltrate the seemingly boundless Soviet airspace. Limited fuel loading meant it only had a standard range of 1,740 miles. This would require the Air Force to base the bomber jets in Europe or devote substantial numbers of tankers just for airborne refueling. Despite these limitations, a lot of hope was still placed in the Hustler. The B-58 couldn't only be the best bomber of the U.S. Forces Strategic Air Command. It also had to show that American aerial technology and innovation were the best on the planet. The Hustler's first flight took place on November 11, 1956, from the Convair facilities at Carswell Air Force Base in Fort Worth, Texas. It lasted 38 minutes and reached an altitude of 63,400 feet. This was also the B-58's public debut. 30,000 people watched astonished as the bomber plane lifted off from the ground, admiring the display of design and speed. The Hustler accomplished its first supersonic flight later that month, turning the B-58 into the first operational bomber capable of Mach 2 speed. The sonic boom sound it made in flight became the Hustler's trademark and was widely reported by concerned civilians underneath its flight paths. The B-58 was one of the first aircraft to take advantage of a fundamental piece of knowledge on overcoming drag in supersonic flight. To break the sound barrier, the pilot had to sweep the wings in an angle that made the plane fly within the Mach cone. A tri-dimensional bow-shaped wave formed around a body flying in the air at supersonic speed. When the wings are within that cone, the airflow around them remains subsonic, allowing for stable flight. The B-58 got its name when Engineering Administrative Supervisor E. Stanton Brown heard about the bomber's performance and said, quote, "Sounds like it'll really be a hustler." The name stuck instantly within the engineering department, and eventually the Air Force made it the aircraft's official name. It was also nicknamed the Champion of Champions. In 1964, the CIA determined that the only aircraft capable of intercepting it was the Chinese MiG-21 Fishbed, and, quote, even then, the chances of a successful hit would be minimal. Although the B-58 was undoubtedly an engineering wonder, the Hustler suffered from an alarmingly high accident rate, costly routine maintenance, and an obsolete mission profile. In total, the Hustler only had an operational life of less than a decade. Even with its exceptional performance, the B-58 was only deployed in 2 operational units. One was at Carswell Air Force Base, and the other was Indiana's Bunker Hill Air Force Base. Just like all Delta Wing planes, it was challenging to fly. It was a machine that demanded respect and attention, but the Hustler's biggest problem was one that engineering improvements couldn't solve. Parallel to the B-58's development at Convair, the Soviet Air Forces developed a high-altitude air defense system built around a surface-to-air missile with command guidance. The S-75 Dvina, known to NATO as the SA-2 Guideline, could reach thousands of feet higher than the Hustler's maximum operating altitude and could strike at speeds faster than any manned jet. Convair's attempt at a solution was to fly lower, but this also meant that the B-58 would have to fly slower, given the denser air at lower altitudes. This defeated the primary purpose of the Hustler's design, its ability to reach Mach 2 speeds. Unfortunately, the plane handled lower speeds poorly. 26 out of 116 produced Hustlers were lost to accidents, resulting in a total loss rate of 22.4% over its service life. Convair maintenance crews reported that for every hour the B-58 flew, it took 35 hours of repairs. The Hustler was a costly program. In today's dollars, a single B-58 would cost $98 million. Some of the test pilots even quit over the constant threat of crashes. They didn't want to risk their lives over such a significant possibility of disaster. Still, the Hustler was very popular with others. Crews around the country wanted to try it out. Not many people got the experience of flying faster than the speed of sound. It was said that being able to tame a Hustler could build a pilot's career. If a bomber could be judged only by its coolness factor, the Hustler would still be in service. But technology is sometimes faster than Mach 2 speed. With a broad set of flaws, price, and several operational difficulties, the B-58 bomber, which was designed for the sole purpose of delivering high-altitude nuclear strikes, had virtually no chance to remain in ranks for a long time. The B-58 never saw combat. In 1970, the Air Force Strategic Air Command retired the Hustler. Political infighting and budget restraints plagued the Convair project since the very beginning. In the end, it just became too expensive to keep funding due to its shocking accident rate. Just as Nixon's presidency started, and America neared a stalemate in Vietnam, a new trend of multipurpose aircraft capable of low-altitude flying began. The Hustler became obsolete. Nonetheless, it is still a remarkable and well-known aircraft. The Hustler won many races, including the Bendix Trophy, Francis Blériot Cup, the Mackay Trophy, and the Harmon Trophy. Perhaps ironically, it was the only bomber to ever receive the Thompson Trophy, which tested low-altitude flying and maneuverability at high speeds. The aircraft set multiple world records, some of which are still unmatched today. To quote Major Howard Bialis, lead pilot of the crew that flew the Hustler to win the Thompson Trophy, quote, "Am I proud to be associated with this great aircraft? You bet your life. Would I do it again? In a heartbeat. Was I ever scared? Always." The General Dynamics F-16 Fighting Falcon has been one of the most popular fighter aircraft ever since it was first introduced in the late 1970s. This legendary all-weather multi-role fighter has been adopted by over 20 nations and received several upgrades. But few know that its original designers made an improved version with twice the firepower, range, and speed. It was called the F-16XL. The aircraft featured a cranked aero delta wing that could carry up to 27 weapons under its wings and twice the fuel storage, and was considered one of the most promising fourth-generation fighters on the planet. There was a lot at stake when it entered the Air Force's Enhanced Tactical Fighter competition, going toe-to-toe with the McDonnell Douglas F-15E Strike Eagle. Few aircraft in history have reached legendary status as the F-16 Fighting Falcon. Introduced in the United States in 1978, the aircraft has since made its way to the air forces of several countries, such as Germany, Belgium, Portugal, Japan, Turkey, Thailand, and even Venezuela. The F-16 has reached global acclaim as an outstanding all-weather multi-role aircraft because of its unique array of features, such as its bubble canopy, its ejection seat with G-force reduction, and its fly-by-wire control system. The aircraft has also been upgraded and adapted to complete various missions involving electronic warfare, dogfighting, or ground support throughout the decades. Overall, it has flown over 400,000 combat sorties in several global conflicts, surpassing 19 million flight hours, and has remained the most acquired fixed-wing aircraft in military service to this day, with more than 5,000 units produced. Still, merely 1 year before the F-16's introduction to the world, the team behind its development began working on another version of the aircraft that was meant to be more powerful and lethal. The F-16 first took to the skies in 1974, and 3 years later, its design team began working on Model 400, or F-16 Scamp, which stood for Supersonic Cruise and Maneuver Prototype. The objective behind the program was to develop a prototype that could be used to experiment with supersonic cruising at a reduced cost. The team did not intend to sell another production fighter. Instead, lead designer Harry Hilliker sought to study the possibilities and application of supersonic transport technologies, or SST, to military aircraft. The program was centered around the effects of laminar airflow at supersonic speeds, along with the causes and effects of sonic booms. Although the F-16 was equipped with powerful afterburners that could increase the thrust that its engine produced to break the sound barrier, the risk was too high. Using afterburners depleted the aircraft's fuel quite quickly, drastically reducing its estimated operational range. The design team knew that they had to make some changes to the standard F-16 Fighting Falcon airframe. If the aircraft could keep its afterburners long enough to maintain its supersonic speed without exhausting its fuel storage, the aircraft would cover more ground in less time and still return to base before fuel was depleted. The men then conducted several theoretical studies about the ideal airframe and wing shape for over 2 years, leading to a partnership with NASA's Langley Research Center to experiment on different models. Using General Dynamics' own funds for internal research and development, or IRAD, Hilliker and his team concluded that a cranked aero wing shape would allow improved lift, range, and maneuverability. Thus, the F-16 Model 400 was born. With the additional 25% lift increase, the improved F-16 would be easier to control at high and slow speeds. The new design had a 50-degree angle near the root of the wing for enhanced supersonic speeds, and a 70-degree angle where the wing extended for subsonic flights. These modifications resulted in twice the surface area of the standard F-16 wings, standing 4 feet longer than expected. But thanks to the more than 3,600 hours of NASA wind tunnel tests, the team managed to apply the modifications without any drag increase in the airframe. However, there were some cons. The moving wingtips and vertical tail for roll control later proved inadequate for low speeds or high angles of attack. Additionally, there was no provision for wingtip-mounted missiles, but because the intent was not to build a tactical fighter, the team was glad the design increased the aircraft's fuel storage and range. Although the new aircraft mainly was based on the F-16's airframe, the changes were substantial. 2 fuselage sections were added at the front and back. Overall length was increased by 58 inches, and the additional cranked arrow wings were made of a special carbon fiber that was lighter by almost 600 pounds. However, the new model still weighed 3,000 pounds more than the Fighting Falcon. It came to 22,000 pounds when empty and 48,000 when at maximum takeoff weight. Wingspan was 34 feet, and height stood at almost 18 feet. The wings gave it twice the fuel capacity of the Fighting Falcon and room for up to 27 hardpoints. This upgrade allowed the model to carry 16 750-pound missiles on its underwing stations, 2 Sidewinder air-to-air missiles on the wing tips, and 4 AIM-120 medium-range missiles on semi-recessed positions. The remaining hardpoints were multi-purpose and could be used for fuel stores and equipment like low-altitude navigation and targeting equipment. In addition, its main armament was a single 20mm M61 Vulcan Gatling cannon for close engagements. All in all, the model offered double the firepower and carrying capabilities of the F-16 Fighting Falcon. 2 prototypes were eventually completed, and by the summer of 1979, the team was confident that the F-16 Scamp had a better range at all speeds when compared to the standard fixed-wing F-16. The U.S. Air Force warmly welcomed the prototype and became a partner of the Scamp program, providing funds for 2 additional prototypes and over 15 Fighting Falcons for conversion. They wanted this aircraft to be a next-generation fighter, but there were other competitors in the market, and it would need to fight its way to the top. Model 400 was then dubbed F-16XL. In March of 1981, the U.S. Air Force announced the ETF, or Enhanced Tactical Fighter Program, to find a replacement for the F-111 Aardvark aircraft. Specifications included a fighter capable of deep interdiction missions without the support of other aircraft or jamming support. General Dynamics Director David Randall Kent was confident enough in the work Hilliker's team did that he decided to submit the experimental F-16XL, pitching it against the McDonnell Douglas F-15E Strike Eagle. The F-15E was also a modified version of an established aircraft, in this case the F-15 Eagle. However, there were differences. While the F-16XL had significant contrasts when it came to airframe and aerodynamics with the standard F-16, the F-15E Strike Eagle was only a modified F-15D 2-seat trainer with the back station altered to support ground attack equipment. General Dynamics and the Air Force began tests in 1982. The F-16XL's General Electric F-110GE 100 turbofan engine offered 17,100 pounds of power and up to 29,000 with an afterburner engaged. The aircraft achieved a maximum speed of 1,400 miles per hour, a cruise speed of 600 miles per hour, and a service ceiling of 50,000 feet, while its rate of climb reached 62,000 feet per minute. The results were unquestionable. The XL delivered twice the range, speed, and firepower of the standard F-16. During a 1983 interview with Air Force magazine, Program Director of General Dynamics Randall Kent said, quote, "The F-16XL flight test program has conclusively demonstrated that the XL performs as predicted. This performance level represents a significant increase in mission capability for USAF. Coupling this with the affordability and low risk of the F-16XL presents USAF with a viable way to increase mission capability while simultaneously growing to a 40-wing TAC force structure." The XL had everything the Air Force wanted for their tactical fighter program. However, the F-15E Strike Eagle was eventually declared the winner. It was stated that the Strike Eagle would be easier to produce than the XL. Existing F-15s would require fewer modifications to convert into Strike Eagles, while existing F-16s would require more work, money, and time to become XLs. Another reason that helped the Strike Eagle was its twin-engine configuration, as it increased the aircraft's survivability during missions. If one engine was damaged, the crew could still return to safety with one engine after engaging in close ground combat. After the contract was awarded to the F-15E, the prototypes of the F-16XL were sent to Edwards Air Force Base in California and remained in storage until 1988, when NASA took them in for research. The first prototype was fitted with an active suction titanium glove that encased the left wing and was taken to Ames Dryden Flight Research Facility. NASA used it to test sonic boom, engine noise, and takeoff performance. The second prototype was fitted with a new General Electric engine and unexpectedly achieved supercruise when it reached Mach 1.1 at 20,000 feet. NASA finished tests in 1999, and the two prototypes were sent to the Air Force Flight Center Museum, where one of them remains on display to this day. Meanwhile, the F-16 continues to successfully serve in several nations, including the United States. During the 1970s, a program was created to ensure that America's allies could face the Soviet Union's air threat. The ensuing FX program would develop a unique model that could confront the MiGs without using any compromising technology that could fall into the wrong hands. Thus, the Northrop F-20 Tiger Shark was born, a light fighter that met all the requirements. But as author Steve Pace pointed out, it was arguably, quote, one of the best fighters that never went into production. During President John F. Kennedy's administration, the U.S. Department of Defense was tasked with finding a fighter aircraft that could be offered to their allies. Through the Mutual Defense Assistance Act, the U.S. would select an inexpensive model that did not feature compromising, leading-edge technology so that it didn't fall into Soviet hands and risk national security. In April of 1962, the U.S. Air Force informed the Secretary of Defense that an aircraft had finally been selected. It was the Northrop F-5 Freedom Fighter. The International Fighter Aircraft Program was created as Soviet MiGs became increasingly common and a significant threat, and the Allies needed an equivalent. The U.S. Air Force then submitted a request for a lightweight fighter that could stand against the MiGs. Among several companies that submitted a proposal, Northrop's F-5 stood out, and an upgrade of the F-5E Tiger II was announced as the winner in late 1970. Over 1,000 aircraft were eventually produced. An initiative eventually stemmed from the 1975 Air Force program FX, to develop a new fighter that would outperform the F-5E. However, the new model could not employ advanced avionics systems currently used in other U.S. aircraft. The ultimate objective was to provide a low-cost export frontline fighter to the nation's allies to compete with the latest Soviet fighter threat, the MiG-21. Moreover, unlike previous programs in the Mutual Defense Assistance Act, the FX would be entirely financed by the private sector. Such companies would be banned from marketing the aircraft themselves, as sales would be handled by the Department of Defense. While Northrop's model would allow U.S. allies to sell the FX fighter without exposing important military advances, the political environment in the late 1970s and early 1980s would place strict restrictions on sales, severely limiting the model's potential. The Northrop F-20 Tiger Shark was an evolution of the F-5E model series of the F-5 Tiger II line. The concept was initially developed under the designation F-5G, but gradually became its own design. The F-20 seemed a lot like the F-5 on the outside, with its sharp nose cone and the cockpit well after the nose section, but not yet midship. Unlike the F-5E, this aircraft had a single General Electric F-404 engine buried in the aft fuselage, with two elongated rectangular intakes along the sides. However, the outtake was a single exhaust chunky ring under the tail rudder. The engine also provided 60% more thrust than the two old General Electric J-85s combined. Consequently, its thrust-to-weight ratio improved from 1.0 to 1.13, its speed was over Mach 2, and its ceiling was over 55,000 feet. The Tiger Shark's initial climb rate was 52,800 feet per minute. Although the F-5E's wing profile remained unchanged, the leading-edge extensions were modified, improving the maximum light coefficient by 12%, while the wing area increase was a mere 1.6%. A single vertical tail fin and low-set horizontal planes made up the empennage, whereas the main wing had swept-back leading edges and straight trailing edges. Plus, the wings were clipped to hold the standard Sidewinder missile, and the wholly retractable undercarriage was a conventional configuration of two main legs and a nose leg. Initially, the aircraft was rather sluggish in terms of pitch. Hence, the horizontal stabilizer was increased by 30%, and a new fly-by-wire system with dual channels was installed. The construction of the F-20 would employ composite materials, and different areas were redesigned during development to use fiberglass instead of metal. There were also plenty of upgrades in the mechanical parts. Its avionics suite was innovative and a considerable improvement from older designs. The multi-mode General Electric AN/APG-67 radar offered several air-to-air and air-to-ground models and was the centerpiece of the sensor system. The older navigation system was also replaced with an entirely electronic version based on a ring laser gyroscope. Therefore, the total time from power on to takeoff was reduced to around 22 seconds, the shortest scramble time in contemporary aircraft, according to Northrop. The cockpit was changed entirely, and beyond visual range capability improved. The new version featured an immense heads-up display, 2 monochrome multifunction displays highly placed on the control panel, and a complete hands-on throttle and stick control system, or HOTAS. This configuration allowed the pilot to keep both hands on the control system while keeping the instrument panel at reach. All these improvements amounted to arguably the most reliable aircraft in service back then. Furthermore, the Tiger Shark was fitted to handle most of the weapons in the U.S. arsenal, from Mark 80 bombs to AGM-65 Maverick air-to-ground missiles, or AIM-9 Sidewinder and AIM-7 Sparrow air-to-air missiles. The F-20's main competitor, the General Dynamics F-16, could not fire the Sparrow until the late 1980s. Like the rest of its F-5 family, the F-20s were equipped with 2 nose-mounted M39 cannons. However, production aircraft might have featured 2 lighter Ford Aerospace Tiger Claw cannons instead, with a higher fire rate than the M39A2 they were based on. But there were also some issues due to the fighter's small size. The aircraft had a shallow ground clearance because of its low-mounted wing, and the landing gear position needed loads placed in the outer ends of the wings, limiting hardpoint weights to 1,000 pounds. Only one hardpoint beneath the fuselage was able to transport a heavier load, such as a single Mk-84 2,000-pound bomb, or even 5 Mk-82 500-pound bombs. Another disadvantage was that its payload and range were limited in comparison to the F-16. But while the F-20 was significantly more expensive than its predecessor, the F-5E, it was less costly than other options on the market, including the F-16. In fact, life maintenance costs were around 50% lower than the F-16. Ultimately, the budget-friendly design was planned to consume 53% less fuel and to have 63% lower operating costs, while being 4 times more reliable than the competition. In late August of 1982, the F-20 had its maiden flight. The flight lasted 40 minutes, and the prototype climbed 40,000 feet and reached Mach 1.04. The results were beyond promising. The first customer came in November, and it was Bahrain. South Korea was also interested in producing the F-20 locally, and some improvements were implemented, expanded fuel capacity, and fiberglass composites to facilitate and support the production. By the end of April the following year, 240 flights were accumulated, and 10 potentially interested nations performed evaluation flights. Several negotiations were simultaneously taking place, which appeared to be a positive sign. Even ace Chuck Yeager said, quote, "Of all the airplanes in the world that I have flown, the F-5 is the most fun to fly." In 1983, a second prototype took to the skies, featuring a complete avionics suite. The test program included the missile essays, and the Sidewinder and the Sparrow were assessed. Several experiments followed with rockets, bombs, and firing rounds. One of the main characteristics of the Tiger Shark was its ability to fly at 124 kilometers per hour at a 35-degree angle of attack. In contrast, the F-16 was limited to 30 degrees. During these flights, acceleration from Mach 0.9 to 1.2 was achieved in 29 seconds, while the climb to 40,000 feet happened in 2.3 minutes. In May of 1983, the Air Force signed an agreement to certify the F-20's performance, airworthiness, and fixed-price program. Meanwhile, the Tiger Shark was already being marketed within the American services. The U.S. Navy was looking for a new fighter for its Top Gun program of dogfight training. They specifically sought an aircraft that could match the current Soviet fighters, but the Navy ultimately went for the F-16. As the Air Force itself did not purchase the F-20, it doomed the line and any further developments, not to mention its acceptance into the global market. Insufficient endorsement from the service was regarded as proof of its value, and the international orders were cancelled. 3 prototypes had been completed, and a 4th was under construction with several new ideas. Still, as Rand Corporation said, quote, "Northrop did not take a prototype approach with the F-20. The first F-20 was intended to be a production-quality aircraft." At the time of the project, Northrop Corporation's private endeavor cost amounted to $1.2 billion, and the model was never sold to a foreign party due to bureaucratic setbacks and lack of support from the government. The company eventually gave up and canceled the project for good in 1986. Prior to the program's termination, the Tiger Shark flew 1,500 flights. However, 2 tragic accidents might have also contributed to canceling the program. In 1984, pilot Darrell Cornell crashed during a demonstration flight in South Korea. And in 1985, Dave Barnes crashed at Goose Bay, Labrador, while practicing for the Paris Air Show. Both pilots blacked out due to excessive G-forces, clearing the F-20 of any fault. As impressive as the F-20's design was, aviation experts agree that it came out at the wrong time, as the F-16 Fighting Falcon, with similar cost and multi-role capabilities, was favored. As such, the Tiger Shark never fulfilled its destiny to become the Cold War era's light fighter star. The McDonnell Douglas X-36 tailless fighter agility research aircraft was built in the late 90s in collaboration with NASA, with the objective to reduce weight and drag while increasing range, maneuverability, and most important, survivability. To achieve all these goals, they decided to get rid of the traditional empennage found on most aircraft, a feat that many contractors and government organizations had tried for decades. But that wasn't its only impressive asset. The aircraft had a remotely piloted design, through which it was flown by a pilot sitting safely on a chair in a ground-based virtual cockpit, with a camera mounted on the plane to provide the view. The unique configuration, which also gave it a one-of-a-kind futuristic look, helped the program move along in a short window of time and be ready in less than 2 years. Its future now rested on either NASA or McDonnell Douglas, which were both impressed with the invaluable yet niche knowledge it provided during its testing phases. During the 40s and 50s post-war period, more efficient engines entered the market and allowed faster speeds than ever before. This was also when semi-tailless experimental aircraft started being built to assess their feasibility. Many scientists believed that a total or semi-tailless design would allow greater stability when flying past the transonic range from Mach 0.8 to Mach 1. However, airframe development at the time was still insufficient to even try to safely control a tailless aircraft. Tailless designs were constantly re-examined during the following decades, as remote computer-controlled fly-by-wire systems could adjust an aircraft's flight controls quickly enough to keep the tailless planes airborne. NASA, which had taken part in developing several experimental aircraft programs that resulted in significant advances to airframe design, also wanted to participate in researching tailless models. In 1994, after about 5 years of studies and wind tunnel testing, NASA and McDonnell Douglas, their largest contractor, agreed to embark on a joint project to develop a prototype fighter aircraft designed for stealth and agility without a tail. The objective was to study new technologies for future tailless low observable fighter designs. The team consisted of employees from McDonnell to build the aircraft and NASA's Ames and Dryden research centers to develop critical technologies and test out the model. The joint venture's top executives and engineers hoped that the tailless research aircraft could dramatically change the design of future stealthy fighters. Named the X-36, the aircraft was built in a 50-50 funded cost-sharing collaboration arrangement with a mixture of advanced, low-cost design and manufacturing techniques provided by Phantom Works, the advanced prototyping arm of the defense and security side of Boeing. The aircraft combined several critical emerging technologies to demonstrate tailless high angle of attack agility for the first time, as well as low observability in a combat-style unmanned configuration. Even though the X-36A was equipped with a GPS-based autopilot, the aircraft was flown by a pilot in a ground-based virtual cockpit, with the view provided by a camera mounted on the plane's canopy. As a result of being a remotely piloted design, the X-36 lacked a real cockpit. Also, because the aircraft would only represent a possible future fighter design, the X-36 was built only to a 28% scale of a standard fighter aircraft, weighing 1,300 pounds when fully fueled and with a total wingspan of 10 feet 5 inches. For flying, the X-36 was fitted with a canard forward of the wing, split ailerons, and an advanced thrust vectoring nozzle, and it was powered by a Williams Research F-112 engine that provided around 700 pounds of thrust. The innovative design, which would take off and land on a conventional retractable tricycle landing gear, promised to reduce weight, drag, and radar signature, all while increasing the range, maneuverability, and survivability of future fighter aircraft. In case of emergency landings, the X-36 could be directed to deploy a dorsal parachute package for a safe recovery. The X-36 also had a state-of-the-art single-channel digital fly-by-wire control system developed by Boeing engineers with commercially available components. Phantom Works officially began building 2 X-36 vehicles in 1994 by using rapid prototyping techniques in the team's St. Louis facility. The small-scale prototype was designed, developed, and built in a relatively short 29 months for around $20 million, less than a tenth of the average cost to develop and test full-scale, human-piloted aircraft. After a 6-month-long intensive flight test program in the summer of 1996, in which the experimental aircraft was suspended on a cable beneath a helicopter, the X-36 finally attempted its first free flight on May 17, 1997. The aircraft went on to perform several dozen flights with and without the help of the helicopter after its maiden voyage. In both Phase 1 and Phase 2 of testing, the X-36 was operational for up to 5 days in a row. According to Mark Sumich, a NASA project manager, this was an unprecedented feat for flight testing and remotely piloted vehicles, which helped the program stay ahead of schedule and under budget. The unique pilotless approach also eliminated the need for expensive autonomous flight control systems, was safer for the remote pilot, and allowed for an aggressive and fast-paced flight test program. Throughout the testing phase, the program met or exceeded all project goals, and it was now referred to as the Boeing X-36 after McDonnell's merger with Boeing in August of 1997. In only 73 days, from May 17th to July 29th, the X-36 conducted its initial testing phase, attempting to verify the aircraft's remote control software, ground station connectivity, data system, and air data calibrations, all in preparation for the more aggressive agility testing in the following stage. Throughout a series of flight tests, the low-cost and fast-paced research vehicle proved the feasibility of using new flight control technologies without a tail. It also showed plenty of potential to improve the maneuverability and survivability of future aircraft. The second testing phase began on August 6th, still at the Research Center in California. During the exercises, the X-36 successfully completed all of its planned high and low G-force agility maneuvers. These tests included 360-degree rolls at angles of attack of up to 15 degrees and several other rapid turning maneuvers. Throughout the entirety of the phase, the X-36 tailless research aircraft continued to perform exceptionally well, proving to be more agile, capable, and maneuverable than all the fighter aircraft in the world at the time. By then, the tailless research aircraft had flown a total of 10 hours and 54 minutes. In an official interview, X-36 program manager Gary Jennings announced the success of the experimental aircraft up to that point, stating that, quote, "After 22 flights, the aircraft continues to perform flawlessly and exceed performance expectations. The maneuvers it has performed so far go beyond the capabilities of the FA-18 Hornet, the top standard for agility in fighter aircraft." After the flight control software was updated with the results from Phase 2, the next one began later that month. Scheduled to conclude in November of 1997, the aircraft further demonstrated performance maneuvers at lower speeds and varied high angles of attack. Then, after thorough and aggressive testing throughout the fall, NASA's X-36A flight test program finally ended, having tested all aspects of the aircraft's operation, flight control software, and full agility performance. The United States Air Force Research Laboratory then used one of the X-36s in 1998 to test its reconfigurable control for tailless fighter aircraft, or RESTORE, flight control software. This unique technology used neural network algorithms to compensate for in-flight changes to the aircraft's aerodynamic configuration. The X-36 eventually performed 2 RESTORE test flights in December of 1998, after which the 2 prototypes were placed in storage for several years. Similar unpiloted technology was also tested simultaneously by the NASA Low Observable Flight Test Experiment, a supersonic and hypersonic unmanned technology demonstrator stealth aircraft, as a joint venture between the organization and the U.S. Air Force. During the 3 stages of testing, the X-36 team successfully developed and demonstrated a functioning tailless fighter design, using several advanced technologies that improve the maneuverability and survivability of possible future American fighter aircraft. However, despite its potential suitability and undeniably effective test program, there were no reports regarding further development of the X-36 or any derived design after it ended in 1998. The state-of-the-art and promising fighter design was surprisingly not pursued by neither NASA nor Boeing, but many experts believe it may be due to the overall costs associated with building a full-scale working prototype, which would be significantly more expensive than a sub-scale model. Still, the technology seen in the Boeing's X-45A unmanned combat aerial vehicle demonstrator is similar to the experience obtained from the X-36 program. After being stored for years, the second X-36 prototype is on display outside the Air Force Test Flight Center Museum at Edwards Air Force Base in California, while the first arrived at the National Museum of the United States Air Force in Dayton, Ohio in July of 2003, and is still displayed today in its Research and Development Gallery. When it got there, then Director Charles Metcalf stated, quote, "As proud as we are to portray Air Force history, we also want to present modern technology, and give our visitors a picture of how today's evolving capabilities are shaping tomorrow's Air Force. The Myasishchev M50 Bounder was a rare Soviet Air Force 4-jet-engine supersonic strategic bomber prototype conceived to strike against the Americans in case the Cold War escalated. The M50 was equipped with 4 engines and enough fuel to handle strategic strike capabilities with a range of up to 10,000 kilometers. It was also capable of achieving speeds of almost 2,000 kilometers per hour and was armed with an arsenal of lethal M61 cruise missiles. However, the M50 revealed a lack of understanding of supersonic flight, and the rise of intercontinental ballistic missiles and the initial victories of the Soviets during the space race soon became a priority for the Russian industry. Stalin himself approved the development of the Bounder, but it came at a considerable cost. When World War II ended, tensions between the United States and the Soviet Union quickly escalated, and the world was suddenly aligned either with the American capitalists or the Russian communists. During the 1950s, these two superpowers began developing nuclear weapons and aircraft capable of delivering their bomb loads at unimaginable ranges that significantly exceeded expectations. Their militaries kept trying to outdo each other when it came to developing top-tier armament and vehicles, and thus the arms race began. Following the end of the war, the Red Army invested significant resources to catch up with the latest weapon developments of the West, and with the help of abducted German scientists and engineers, the Soviets quickly developed their own nuclear bombs and other weapons of mass destruction. One of the earliest priorities was developing supersonic strategic jet bombers that could succeed Soviet aircraft used during the war, as the nation's doctrine during the conflict relied heavily on tactical air support and not strategic bombing. The 4-engine bomber Petlyakov PE-8 was only produced in small numbers, and its role was minimal in the fight against the Germans. This Soviet bomber could barely hold its own against the American B-17 or the British short Sterling bombers. Following the first successful Soviet nuclear bomb detonation in 1949, Stalin finally approved the development of a long-range strategic bomber that could deliver nuclear payloads. As the Soviets set out to build a long-range strategic bomber, they realized that they lacked the knowledge of American military engineers and resorted to their spying and copycat abilities for inspiration. Soviet specialists then reverse-engineered several American Boeing B-29 superfortresses that were forced to land in Siberia to develop their own bomber. The Soviet version was called the Tupolev Tu-4 and was designated as Bull by NATO. These preliminary attempts at building effective bombers were beneficial for the Soviet industry. Although they did not hesitate to deliberately steal from American designs, they had plenty of ideas of their own, and the Soviet Air Force soon realized that the Tupolev Tu-4 was just as vulnerable as the B-29. During the Korean War, Soviet MiG-15 jet fighters easily shot down plenty of American B-29s. Hence, the Soviets knew that their version would be just as vulnerable as the American fighters. Then, as the US Air Force began developing the Convair B-58 Hustler bomber in the early 1950s, the Soviet Air Ministry set out to build its own Mach 2 bomber. However, the Soviets were already behind the Westerners when it came to its bomber arsenal, as the United States already had operational Boeing B-47 Stratojets. At the same time, the British were almost done with their advanced Vickers Valiant and the Short Sperrin. The concept of supersonic aircraft had taken hold of the global aircraft industry. Journalists and war correspondents continually filled the imaginations of thousands of readers with fantastic visions of aircraft that could effortlessly travel with the speed of sound. But engineers knew the complexity of supersonic capabilities, especially the Soviets. The Soviet Experimental Design Bureau, under the control of Vladimir Mikhailovich Myasishchev, worked hard to develop an authentic long-range, high-altitude bomber. Simply designated DVB-102, this model had only 2 engines instead of the usual 4 of most long-range bombers. However, the prototype never made it into production, and Myasishchev and the Experimental Design Bureau of the Air Force were disbanded. Still, Myasishchev would not give up, and would ultimately come up with an idea that would translate into a worthy long-range strategic bomber for the Soviet Air Force. Vladimir Myasishchev spent several years drafting different concepts for strategic bombers, and one of them finally made it onto Stalin's desk. The dictator himself said, quote, "Let's believe Comrade Myasishchev and entrust him with developing such an aircraft." Myasishchev was then cleared to develop the bomber and appointed head of the program. The aircraft's requirements included that it needed to be powered by 4 axial flow turbojets with a maximum speed of 850 to 950 kilometers per hour and an approximate range of at least 10,000 kilometers. In addition, its payload capacity, which ranged from nuclear weaponry to standard missiles, needed to be 5 tons. The specifications were aggressive, but Myasishchev was committed to the project. After studying numerous designs, Myasishchev settled for an aircraft with all-swept flight surfaces, conventional tail assembly, bicycle landing gear, and 2 turrets for defensive armament. 1 man turret would be placed at the tail, with a remote-controlled one behind the cockpit on top of the airframe. Work on the design began in 1952, and the prototype was finished in early 1953. The aircraft, simply dubbed M4, flew for the first time on January 20th with a crew of 7. In March of 1954, the M4 Bison flew publicly for the first time during the Moscow parade. NATO officials witnessed the long-range bomber and classified it with the codename Malot. Although the aircraft did not break any records, it earned Myasishchev the commission to develop another bomber capable of striking the United States and returning to the Soviet Union. This bomber was codenamed M50. The M50's airframe resembled an enlarged Mikoyan-Gurevich MiG-21. It comprised a slender fuselage with a delta wing mounted in the middle and a circular cross-section with a bulge that ran all the way to the spine and fuel lines. Most of the fuel was stored in the fuselage. It was transferred between the aft tanks to counter-trim charges as the M50 altered between subsonic and supersonic speeds. The wings had a triangular design and had a wingspan of 25 meters. No fuel was stored in them as they were extremely thin. A pylon-mounted engine was placed under each wing near the wingtips, and a second one was mounted at the tip of each wing. The wings contained rectangular, double-slotted flaps and outboard ailerons. When the M50 landed, the ailerons dropped down to drastically reduce the aircraft's speed. The weapons bay was large enough to carry M61 cruise missiles, which were 11 meters long. Overall, the M50 itself was 58 meters long and 8.25 meters tall. The bomber weighed 78,860 kilograms when empty. Fully loaded with a bomb load of 5,000 kilograms, its weight increased to 145,000 kilograms. Its approximate ceiling was 14,000 meters, with an estimated range of 13,000 kilometers, plus the increased range of the M61 missiles. Its top speed was 1,960 kilometers per hour, or Mach 1.84. The 2-man crew would sit at the nose of the M50 in a tandem configuration, and each man had access to downward ejection seats. Entry and exit were done through the bottom hatch, located at the bottom of each seat. Both men had to wear pressure suits, as the aircraft was designed to fly at high altitudes. Construction of the M50 bomber began in the first months of 1956. Later in development, 4 non-afterburning Dobrynin VD-7BA turbojets of 95.61 kilonewtons were added to bolster speed. During testing, the design team encountered unforeseen problems, such as deformation of the thin wings during high speeds and stability problems at supersonic flights. In October of 1958, the aircraft was sent to the Zhukovsky Flight Test Center. After several tweaks, the M50 took to the skies again on October 27, 1959, with pilots A.S. Lipko and Kikola Goryanov at the controls. The first tests were conducted successfully, but on May 12, 1960, the M50 collided with a 3ME bomber prototype. The aircraft was then grounded and repaired 2 months later. Engines were replaced to bolster speed, but supersonic strength was insufficient. After adding weight due to several modifications, the maximum speed did not go past 1,100 kilometers per hour. Even worse, fully loaded, the M50 could only attain a range of 3,500 kilometers out of the expected 9,000. Still, the aircraft was able to attract the attention of NATO forces when it was displayed at the Moscow Air Show. The Westerners classified the aircraft as bounder, in reference to something that's trying to present itself as above its station. This was the last flight of the M50 before it was replaced by an improved version called M52. The new model featured a 3-man crew, twin-tail machine guns, and provisions of additional cruise missiles under the wings. But the end of the strategic bombers was just around the corner. With the increasing importance of intercontinental ballistic missiles, long-range strategic bombers suddenly became obsolete. Soviet Premier Nikita Khrushchev then canceled all programs related to bombers to focus on the development of these missiles and the Soviet space program. The Myasishchev company then closed its doors in 1960, and its personnel was assigned to other programs. The M50 prototype was initially parked at the Romanskoye Airport in Zhukovsky, but it was later relocated to the Central Air Force Museum in Monino, where it can be found today. The Bounder is still remembered as a costly failure that revealed the Soviets' scarce understanding of supersonic flight. In the fall of 1974, the Space and Missile Systems Organization conducted an air-launched ballistic missile test. The Minuteman ICBM weighed 86,000 pounds, and the only aircraft up to the task was the recently unveiled Lockheed C-5 Galaxy. The immense military transport aircraft conveyed the gigantic mine and dropped it from 20,000 feet over the Pacific Ocean, proving the feasibility of launching an intercontinental ballistic missile from the air. Although it was first conceived in the 1960s, the massive piece of engineering continues to serve in the Air Force and has taken part in several unique missions, including transporting Marine One to any place the President travels, within the United States or overseas. The unusually sizable aircraft also played a pivotal role in the development of the first operational aircraft to be designed with stealth technology, a mission so secretive that the C-5 can only fly at night to transport each of the airframes. Early in the 1960s, several top aviation companies investigated heavy jet transport concepts. At the time, the industry strived to create a new aircraft to replace the Douglas C-133 Cargo Master and complement the Lockheed C-141 Starlifter. Besides enhanced performance, the U.S. Army was looking for a transport vehicle with a larger cargo bay than its existing aircraft, which were unable to carry outsized equipment. Finally, in 1963, a new concept came to light. It was the CXX. Unlike earlier designs with 6 engines, the new one had only 4. The aircraft would weigh 550,000 pounds, with a maximum payload of 180,000 pounds, and the cargo compartment would measure 17.2 feet wide, 13.5 feet high, and 100 feet long. On the other hand, the aircraft had to reach a top speed of Mach 0.75, or 500 miles per hour. As such, the USAF conducted a study that determined the model would need high bypass turbofan engines to fulfill thrust and fuel efficiency requirements. When the conditions were officially issued in a request for proposal in the spring of 1964, several major companies submitted designs for what they called the Heavy Logistics System, or CXHLS. Among the top competitors were Boeing, Douglas, General Dynamics, Lockheed, and Martin Marietta. As for the specialized engines, General Electric, Curtiss-Wright, and Pratt & Whitney proposed different ideas that shared a number of features. The Air Service considered Boeing's design the top choice, but Lockheed's proposal was considerably cheaper. Thus, in September of 1965, Lockheed emerged as the winner and was awarded the contract, with their aircraft being powered by General Electric's revolutionary TF-39 engine. Notably, while Boeing's model lost the military bid, the company went on to develop an equally successful civilian airliner, the Boeing 747. On March 2, 1968, the first C-5A Galaxy rolled out of the manufacturing plant in Marietta, Georgia. The immense transport, as long as a football field and as high as a 6-story building, became the world's largest aircraft, along with its lifelong rival, the Boeing 747, and the Antonov AN-124. The model has front and rear cargo openings that enable it to be loaded and offloaded simultaneously. Both nose and rear openings span the cargo compartment's full width and height to allow drive-through loading and unloading of vehicles. In addition to carrying both tracked and wheeled vehicles, the enormous aircraft can also be easily loaded with bulky equipment. Remarkably, the Galaxy showcases a 28-wheel undercarriage configuration with a kneeling system that lowers the aircraft's cargo floor to truck bed height. Furthermore, the power plant consists of 4 turbofan engines mounted under the wings. Back then, GE's engine concept was innovative in its unmatched bypass ratio. While no other engine before had less than 2-to-1 ratios, the TF-39 delivered a ratio of 8-to-1, thus increasing engine thrust and fuel efficiency. Finally, by the end of June 1968, aircraft serial number 66-8303 took to the skies for its first flight, piloted by Leo Sullivan, with call sign 8303 Heavy. The flight test phase then began, and the new aircraft provided the U.S. Air Force with a heavy intercontinental range strategic airlift capability that could carry outsized and oversized loads, and all air-certifiable cargo. Even so, as the testing revealed, the model had a higher drag divergence Mach number than expected, and the maximum lift coefficient also varied from predictions. Moreover, weight became a serious issue, even on the drawing table. During the following years, the Mammoth vehicle would experience wing failures at less than the required 150% limit load. Therefore, it received a passive load reduction system comprising uprigged ailerons, but the maximum allowable payload was reduced nonetheless. In truth, no more than 10% of the 79 airframes were expected to reach the end of their service lives without cracking the wing. During static and fatigue testing, cracks appeared in the wings of several aircraft, and the C-5A fleet was forcibly restricted to 80% of maximum design loads. The program soon became the subject of congressional investigation, as it was the first development program with a $1 billion overrun. And as Lockheed experienced severe financial difficulties, production was nearly brought to a halt in the early 1970s. Nevertheless, the U.S. government intervened, offering loans to keep the company operational. The colossal transport then went into production, and not much later, into service. Lockheed finally delivered the first operational C-5A Galaxy to the 437th Airlift Wing, Charleston Air Force Base, South Carolina, in June of 1970. In the words of aviation historian Robert Dorr, quote, "After being one of the worst-run programs ever in its early years, it has evolved very slowly and with great difficulty into a nearly adequate strategic airlifter that unfortunately needs in-flight refueling or a ground stop for even the most routine long-distance flights." In the early 70s, the Iranian government became interested in the C-5 and offered $160 million to produce the model, as it planned to purchase the aircraft. However, the prospect was put to an end by the Iranian Revolution. Even so, the financial support, coupled with President Ronald Reagan's military policy, helped to restart the production, and a renewed version of the Galaxy was soon delivered, the C-5B. Going into the 80s, the C-5B received an expanded airlift capacity, as well as over 100 improvements and additional system modifications that enhanced its predecessor's reliability and maintainability. Throughout the decade, 50 B models were added to the fleet of 76 A examples in the Air Force's airlift force structure, and 2 space cargo-modified C-5Cs were also delivered. Their modifications included the removal of the troop compartment, the redesign of the aft pressure door and bulkhead, and the widening of the aft doors to make room for the space shuttle's cargo container. The Galaxy would then undergo a more extensive optimization, after a study showed that 80% of the C-5's airframe service life was remaining. As such, the Air Mobility Command began an aggressive program to modernize the Galaxy fleet in 1998. The C-5 Avionics Modernization Program sought to upgrade the avionics, including the improvement of communications, navigation, surveillance, and air traffic management, so that the aircraft could comply with national and international airspace standards. It also included modern safety equipment and a new autopilot system. One of the main features of the modernization plan was a comprehensive reliability enhancement and re-engineering program that renovated the engines to General Electric CF6 ADC2 L1F commercial ones, increasing thrust by 22%. Moreover, the takeoff roll was reduced by 30%, while the climb rate was increased by 58%. In addition, the fleet was now quieter and with enhanced system integrity. Able to carry significantly more cargo over longer distances, the modified C-5s became C-5M supergalaxies, the renovated transports that would extend the C-5's operational capability well into the 21st century. The C-5 airlifters supported the Air Force across all major military operations, from Vietnam, Yugoslavia, and Afghanistan to the Yom Kippur War and the Gulf War. Moreover, the Galaxy has also been deployed in humanitarian aid missions and disaster relief operations, in addition to the space program. But perhaps most notably, the imposing aircraft was employed to aid the U.S. Air Force with a highly secretive mission. During the mid-1980s, the Air Force was developing the revolutionary Nighthawk stealth fighter. The Air Service was in need of integrating the so-called Black Jet into regular operations, but unfortunate mishaps with losses of aircraft and pilots in night sorties complicated the transportation of the unrevealed machine. The powerful C-5 was then chosen to transport the Nighthawk, flying the disassembled aircraft from the Skunk Works facility in Burbank, California, to Groom Lake in complete secrecy. Upon arrival, the jet was reassembled and test-flown prior to its public unveiling in 1990. To this day, the Airlifter is still the largest aircraft in the Air Force's inventory, and as a strategic transport aircraft, its primary mission is to move cargo and personnel for the Department of Defense. Among B, C, and M variants, the Air Force still operates a fleet of 52 C-5s stationed at Dover Air Force Base, Delaware, Travis Air Force Base, California, Lackland Air Force Base, Texas, and Westover Air Reserve Base, Massachusetts. Building upon the legacy of the C-5's heritage, the modernized C-5M is equipped with 5 sets of landing gear, but it includes a state-of-the-art maintenance diagnostic system that enables the record and analysis of data for more than 7,000 test points, reducing both maintenance and repair time. The Super Galaxy can also carry oversized cargo over intercontinental ranges and features full-width drive-on ramps that enable double roads of vehicles to be transported. It can also load and offload cargo with reduced transfer times, and the M variant can even take off and land on relatively short runways compared to its predecessor. The C-5M can carry a load of 281,001 pounds across 2,150 nautical miles. It can then offload and fly to a second base 500 nautical miles away from the first destination without needing aerial refueling. In fact, with aerial refueling, the aircraft's range is allegedly only limited by crew endurance. As for the future, the Super Galaxy aims to extend the fleet's life into the 2040s. But as the Air Force envisioned, further modernization efforts will include the incorporation of advanced weather radar, mission computing, communication systems, and air traffic management to enhance survivability. In the early 1990s, the U.S. Air Force launched a new program to build a next-generation advanced tactical fighter. This gave way to a legendary competition between Lockheed and the Northrop Corporation that created the outstanding YF-23. The aircraft had a radical design thanks to its diamond-shaped wings and V-tail, which immediately differentiated it from its competitor. The fighter reached supersonic speed and had been designed to fly undetected to enemy radars. Even though it was a unique aircraft, the U.S. Air Force selected its rival, the Lockheed F-22 Raptor. Many say the Raptor won because it was more agile, easier to maneuver, and could attack at a steeper angle. But in reality, Northrop's issues with previous contracts and its poor standing with the Pentagon also gave Lockheed the upper hand. The competition between both companies shows that a good reputation can sometimes be as important as groundbreaking design or superior technical specifications. In 1981, the U.S. Air Force started the Advanced Tactical Fighter program to develop a next-generation air superiority fighter. At the time, the Soviet Union had developed aircraft like the Sukhoi Su-27 and the Mikoyan MiG-29. These were meant to compete with the fourth-generation fighters of the U.S., like the F-15 Eagle. After American reconnaissance satellites caught the first glimpse of the advanced Soviet prototype fighters, discussions with U.S. airspace companies began. To face the Soviet threat, The Air Force envisioned a program that could combine emerging technologies and concepts like stealth, supercruising, and short takeoff and landing. By 1984, the program finally defined the new fighter's requirements: supercruise speed, a maximum takeoff weight of 50,000 pounds, and a mission radius of 800 miles. A year later, the Air Force issued a request for proposals. Grumman, Rockwell, Boeing, General Dynamics, Lockheed, Northrop, and McDonnell Douglas each presented their plan in 1986 and later grouped into two competing teams. Northrop and McDonnell Douglas were selected as finalist partners with their YF-23A design. They were challenged by Lockheed, Boeing, and General Dynamics with the YF-22A. Both teams were given 50 months to build and test their prototypes. The Air Force anticipated buying 750 fighters. A variation of the winner's aircraft would also be used by the U.S. Navy to replace the F-14 Tomcat. The winner would go down in history as America's air superiority fighter of the 21st century. The Northrop YF-23 was designed to focus on the U.S. Air Force requirements of stealth, survivability, and ease of maintenance. Therefore, agility wasn't one of its priorities. The fighter had a range of about 2,800 miles, which could be extended with in-flight refueling. Two prototypes of the aircraft were built: the Black Widow II and the Grey Ghost. The Black Widow flew with Pratt & Whitney engines and had its maiden flight on August 27, 1990. It was painted in charcoal gray and carried a painting of the characteristic red markings found in Black Widow spiders. Its radar cross-section signature also looked like a spiderweb. The second prototype, the Grey Ghost, flew with General Electric engines and was painted in two different shades of gray. The aircraft had diamond-shaped wings and an all-moving V-tail that gave it an unconventional appearance. By focusing on stealth, Northrop designed the plane with a radar-evading profile and a system of turbofan engines that prevented detection by infrared missiles. The YF-23 had a cockpit placed near its nose and fit only one pilot. To reduce costs, the aircraft shared its cockpit and nose wheel components from the F-15 Eagle and the FA-18's main landing gear. This eventually put it at a disadvantage with its rival, which had more advanced cockpit technology and better electronics. However, the aircraft's design was innovative in many other ways. The plane needed to fly at supersonic speed without needing an afterburner, while also maintaining low observability. To achieve this, the Grey Ghost was designed with a boundary layer control system consisting of panels with small holes drilled in them. This system sucked in the boundary layer air before it entered the air intake. Conventional air intakes, in contrast, often needed to be separate from the fuselage, reducing stealth. The weapon bay configuration was also unique. It was a deep coffin-like cavity installed between the cockpit and the air intakes, covered by two swinging doors. There, the aircraft could carry 3 staggered AIM-120s and 2 AIM-9s attached to the bay doors. However, the launch system was never installed in the prototypes. As innovative as it was, the configuration also had one significant defect. If one of the missiles jammed, the ones behind it would become impossible to use. The Northrop team was very confident in their aircraft. John Schupek, who designed the back end of the plane, said to the National Interest, quote, "Northrop ATF team was really proud of our aircraft. We absolutely knew that it was the better of the two airplanes." Parallel to the creation of the Grey Ghost, Lockheed was developing the YF-22 Raptor. Both aircraft went through a series of evaluations, including 11 months of flight tests. The Grey Ghost supercruised twice with different engines. The prototype reached a top speed of Mach 2.1 and a maximum angle of attack of 25 degrees. Despite having a weapon bay, no missiles were fired during the tests. In total, the plane flew for 65.2 hours. In contrast, during one impressive test, the Raptor fired AIM-9 Sidewinder and AIM-120 AMRAAM missiles from its internal weapons bays. Its maximum speed was also over Mach 2, although the Grey Ghost was generally considered a faster plane. The YF-22 accumulated 91.6 hours of flight time. On April 23, 1991, the Air Force announced the Raptor as the winner of the program. The YF-22 and the YF-23 were considered equally good. They could maneuver at the same trimmed and high angle of attack. The two of them could also carry 8 air-to-air missiles internally. Although they were both considered magnificent designs, the YF-23 was actually seen as a better performer overall. Northrop's design was also viewed as superior, thanks to the sleek lines of the aircraft. So why did the Raptor beat the Grey Ghost? In the end, it was a matter of credibility and not technical superiority. Experts agree that Lockheed was better at marketing their aircraft and taking advantage of its competitors' weak spots. Northrop had been suffering from 4 years of a bad reputation due to considerable cost overruns while building the B-2 Spirit stealth bomber. The company was even indicted in falsifying tests on a nuclear weapons guidance system and lost a contract to produce the MX missile guidance system. After a dozen congressional committee hearings and Pentagon audits of all their programs, Northrop's image was irrevocably damaged. Lockheed succeeded in making the Air Force think they could manage the fighter program better. As the defense security budget suffered after the end of the Cold War, the Air Force needed to convince Congress that the program was in the best hands. It also didn't hurt that the Lockheed bid was substantially lower. After the contract was awarded to Lockheed, members of the Air Force confirmed that they had more confidence that the company could deliver the aircraft at the estimated cost. In an interview with the LA Times, aerospace analyst Paul Nisbet said, quote, "Northrop has been under the gun for years. The Pentagon does not want to spend its political hay by running against the grain." Lockheed also succeeded in showing off the capabilities of their fighter. Thanks to a brisk flight test schedule, the company demonstrated how well the Raptor performed in dogfights, how it could attack at an angle of 60 degrees and pull sharp 9G turns. When Air Combat Command pilots witnessed Lockheed's demonstration, they were immediately enamored with their fighter. Although the Grey Ghost could make the same maneuver, they failed by simply not showing it off. Other theories state that Lockheed was selected because it had no new fighter programs, and the United States wanted to keep it alive as an airframer. On the other hand, Northrop already had the FA-18EF and a very expensive B-2. In the end, the YF-22 won the competition and eventually developed into the F-22 Raptor. The aircraft entered service in 2005 and is currently considered a fundamental element of the U.S. tactical air power. But after the fall of the Berlin Wall and the disappearance of the Soviet threat, the Air Force reduced the number of F-22s it initially planned to buy. Meanwhile, Northrop kept building the fighters that eventually became more popular as years went by. Looking back, experts agree that the YF-23 would have performed just as well, but the Grey Ghost had better stealth and longer range at a supersonic speed. Those qualities would have made it a better adversary against new potential threats, like the Chinese J-20 and the Russian PAK-FA. The innovative weapons bay configuration of the Grey Ghost would have also been highly valued nowadays. Indeed, similar designs are still used 3 decades later. After remaining in storage until 1996, the Grey Ghost was sent to the National Museum of the U.S. Air Force and to the Western Museum of Flight in Torrance, California. The planes have been refurbished, and sometimes they get released for tours. Later on, a naval variant of the F-23 was proposed to replace the F-14 Tomcat. The NAT F-23 had vital differences, like conventional twin tails and a diamond wing positioned far in the back. The aircraft was meant to carry Hughes AIM-54 Phoenix air-to-air missiles and be a similar size as the Tomcat. Eventually, the program was scrapped after the Navy decided to modify the F-14 to be able to operate it until the year 2015. In 2004, Northrop Grumman presented a YF-23-based bomber for the U.S. Air Force, and 4 years later, that project was scrapped in favor of a long-range bomber, and later on, for the next-generation bomber program. Meanwhile, the Grey Ghost has won a legendary status in military aviation circles. Rumor has it that the design based on the aircraft lives in the clandestine realm. Northrop Grumman and Lockheed have competed many times since, and have shown they're both still going strong. In 2015, Northrop beat a team formed by Boeing and Lockheed to build a new generation stealth bomber for the U.S. Air Force. The $55 million B-21 Raider will start flying in 2040. Soon, however, we might see both companies compete again to build the replacement of the Raptor. As part of a plan to build a strategic bomber for deep penetration and nuclear bombing runs during the Cold War, North American Aviation created a stunningly futuristic prototype for its time, the XB-70 Valkyrie. Designed for the U.S. Air Force Strategic Air Command in the 1950s, the Valkyrie was capable of achieving Mach 3 while flying at an astonishing 70,000 feet. The Air Force expected its new aircraft to be immune to jet interceptors. The Valkyrie's speed would require constant switching between radar stations, making it nearly impossible to track. Nevertheless, the project would eventually come under pressure due to the Soviets' development of anti-aircraft missiles that negated the bomber's height and speed advantages. The aircraft's designers also failed to foresee the development of intercontinental ballistic missiles that could reach even higher speeds and altitudes unparalleled for nuclear delivery. The XB-70 would become a beautiful but unnecessary piece of aviation technology, and its fate would be sealed after a tragic accident involving the XB-70's second prototype. The XB-70 Valkyrie was an experimental aircraft developed by North American Aviation. Its features were remarkable. Notably, its size was the largest of any type of plane in the history of aviation. The Valkyrie's airframe featured a long fuselage with a horizontal stabilizer placed behind the crew compartment. It had delta wings swept at 65.5%. To grant greater lateral directional stability, its wing sections could be folded down during flight. The airplane had a movable outer windshield explicitly designed for high-speed flights to reduce drag and increase visibility. The fuselage was constructed with riveted titanium, as was the aircraft's covering. The rest was made almost entirely with stainless steel, its surface brazed with the stainless steel honeycomb material. To power the plane, 6 General Electric YJ933 turbojet engines were installed, each with 30,000 pounds of thrust. Inside the engines, it could maintain efficient airflow due to geometric inlets. Flying at Mach 3 at altitudes of 70,000 feet, it became the world's largest high-speed experimental aircraft. Data collected from its testing would serve to plan for future military and civilian designs. The Valkyrie program's primary goals were to collect data on its stability and handling characteristics. They wanted to assess its response to turbulence and examine its aerodynamic and propulsion systems. Furthermore, operators sought to record noise and airflow friction to determine the extent of noise pollution emanating from the engine during takeoff, landing, and taxiing. The aircraft was escorted by a TB-58 during its research flights. That plane was chosen due to its ability to dash at Mach 2. In March 1967, NASA took over management of the program they'd shared with the Air Force. Only 2 XB-70A prototypes were built by North American Aviation. On September 1, 1964, its maiden flight took off from Palmdale, California, and landed at Edwards Air Force Base. Tests of the aircraft's airworthiness took place between 1964 and 65, conducted by test pilots from both North American Aviation and the U.S. Air Force. The second prototype was built with a few adaptations recommended by the NASA Ames Research Center in Moffett Field after wind tunnel tests. One of the findings revealed that the first prototype had poor directional stability when flown at speeds beyond Mach 2.5, which led to it being a prototype that only carried out a single Mach 3 flight. Therefore, the second prototype adopted 5 additional degrees of dihedral at the wings. Both the Air Force and NASA signed a joint agreement to use this newer prototype to conduct high-speed research flights. This would lead to new projects through the American Supersonic Transport Program, or SST. Unfortunately, these plans were partially disrupted by one of the best-known and most tragic accidents in the history of military aviation at the start of 1966. President John F. Kennedy officially endorsed the creation of an American supersonic transport through a signed initiative in 1961. The hope was to create a commercial transport aircraft to ferry civilians at 3 times the speed of sound. This aviation dream began in the 50s when it first became possible from a purely technical and mechanical standpoint. Such developments were contested due to challenges with noise generation, high development and construction costs, increased fuel consumption, environmental concerns, and value to the consumer. Still, they present a possible future for aircraft development that is still considered to this day. As part of the initiative, the Flight Research Center at Edwards Air Force Base, known today as the Dryden Flight Research Center, began test flights with a Navy A-5A Vigilante in 1963. They started by studying the effects of landing a high-speed aircraft in the vicinity of heavily crowded air traffic. The pilots would approach the base, but land at LAX to establish more realistic simulations using supersonic transport planes in a high-volume commercial environment. As a follow-up to the initial effort, they would start using the Valkyrie. The XB-70 was considered an enormous plane for the period. The cockpit's height was 3 stories tall, while its delta wing spanned 105 feet, with a body of 185 feet. As stated before, it used 6 powerful General Electric YJ93 heat engines that could fly 3 times the speed of sound, and the airframe was constructed from stainless steel rather than aluminum, adding significant weight. Furthermore, the design featured modern aerodynamic elements such as canards and sloping wingtips. Despite all of this, the plane never made it into production. The Air Force wanted to hand over the second prototype to NASA in June 1966 for these research purposes. However, they first wanted a photo shoot. General Electric was particularly interested in a group formation photo with the planes that used its jet engines. For the photo shoot, an F-48 Phantom, YF-5A Freedom Fighter, F-104N Starfighter, T-38A Talon, and the second prototype of the XB-70 were brought out to the Californian desert by Edwards Air Force Base on June 8, 1966. To photograph the lineup in flight, a pilot flew a private Learjet owned at the time by none other than Frank Sinatra. The F-104 flew to the right of the XB-70 by Flight Research Center Chief Pilot Joe Walker. Unfortunately, and perhaps unintentionally, he steered the F-104 too close to the Valkyrie. The Starfighter clipped its right wingtip, which caused it to roll up and over, hitting the right vertical fin and tearing off the left. Then, as the ultimate consequence, the Starfighter exploded into a ball of flames and veered to the left. Walker was killed. For about 15 seconds, it seemed the Valkyrie would be fine, as it continued to fly straight at altitude. Then it began to slowly spiral. Pieces of the wing flew away, and fuel leaked out of the sky. Reportedly, one of the chase pilots yelled over the radio, quote, "Eject! Eject!" But Air Force Major Carl Cross couldn't. The pilot, Alvin S. White, managed to get out before the plane crashed into the hills. The investigation later reported that the wake of the Valkyrie's vortex wingtips were to blame. While the science behind vortices wasn't as well researched at the time, all that was known was that the micro-tornadoes emerging from the plane's wingtips caused lethal damage. Furthermore, the Air Force concluded that the F-104 was unable to see the XB-70's wings from their position unless the pilot uncomfortably turned his head. Even today, the Valkyrie holds the record for being the most massive and most heavy plane to ever fly at Mach 3. It proved what it set out to. The high altitude, high speed, and performance of the strategic bomber could outfly its predecessors and safely evade Soviet interceptors. Yet it could not outrun the technology of surface-to-air missiles capable of tracking their targets while in flight. Attempts to salvage the Valkyrie as a penetrator capable of flying under the range of anti-aircraft missiles also proved fruitless, as it was unable to travel faster than Mach 0.95 at low altitudes. The loss of the second prototype marked a significant turning point in the project's existence. Only the less capable first prototype could provide the necessary and valuable data for the research program. The remaining plane flew for 2 more years, focusing on sonic boom data tied to the supersonic transport aircraft program. The data was incredibly valuable until the program was cancelled. Currently, it's temporarily resurfaced as part of the development of Lockheed Martin's X-59 Quest, a 2016 low-boom flight demonstrator program scheduled for delivery in late 2021 and hopefully ready for flight tests in 2022. Only 2 XB-70 prototypes were completed at North American Aviation. The cancellation from the Kennedy administration stemmed from the increasing worry that manned bombers would soon become obsolete platforms. Since bombers are still used, these concerns, paired with the high cost of the program, disenchanted investors. The U.S. Air Force eventually gave up the B-70 aircraft. The program was officially canned in 1961. At that point, the development turned into a NASA research study on the effects of long-duration speedy flights. The 2 prototypes built were used for supersonic flight tests between 1964 and 1966. The tragic interruption of XB-70 No. 2 was due to its crash. The remaining Valkyrie bomber was prepared for a museum. This, the only surviving model, series number 62-0001, is now permanently housed at the National Museum of the U.S. Air Force in Wright-Patterson Air Force Base close to Dayton, Ohio. The plane was flown to Ohio upon the conclusion of the testing program on February 4, 1969. It became their signature aircraft at the museum, featured on their letterhead, and as the main object in the design for the Valkyrie Café. In 2011, the plane was placed on display at the museum's Research and Development hangar, where other experimental aircraft are. The only XB-70 remaining was moved to the 4th hangar near the end of October 2015.